everyone. My name is Katrina Whipple, and I'm an instructional coach at Carter Middle School. It is so good to be with you today, and we are going to do some 8th grade math together.
Today we are going to look at the standard 8EEA1, which says that we should know and apply the properties of integer exponents to generate equivalent numerical expressions. So we're going to look at numbers who have exponents that are both positive and negative, and talk about the different ways that we can simplify these expressions to create an equivalent expression.
Okay, well, let's start by reviewing exponents. We started seeing exponents for the first time in 5th and 6th grade, and all of those exponents were positive exponents. A positive exponent just tells us how many times to multiply the base as a factor. So remember, the base is this number here, and the exponent is the number that tells us how many times we need to multiply this. The most common mistake that I've ever seen is that we say, well, the base is 4, and I need to multiply it 3 times. And we see this. No, no, no. Remember, always go back and check yourself. It is not 4 times 3. It is 4 times 4 times 4. And sometimes, if you need to rewrite that and write the whole thing out so that your brain doesn't make that mistake, go ahead and do it. It's okay. So 4 times 4 times 4. Also remembering to not count by 4s. We know that 4 times 4 is 16, and 16 times 4 is 64. So what was new to us this year was that we started to see some negative exponents. So the negative exponent just tells us how many times we need to divide. So an easy way to look at this one is to say, well, I know I have to divide. So I'm going to divide 1 over 4 times 4 times 4. So 4 to the negative third power is 1 over 4 times 4 times 4. Well, 4 times 4 times 4, we just saw over here, is 64. So 1 over 64. So a very, very similar process. It's just how do we rewrite that to show a slightly different piece of information. All right, so now let's move forward and look at how we can use these exponents together. So we're going to spend just a little bit of time talking about multiplying exponents. So right here we have two whole numbers we've got the same base and different exponents. So I'm going to think about this in terms of each piece. So the 2 squared here is the same thing as 2 times 2. So now let's look at 2 to the third power. 2 to the third power is the same thing as 2 times 2 times 2. So if we were going to simplify that, I'll go ahead and bring my multiplication symbol down. I could say that 2 squared and 2 to the third power is the same thing as 2 to the 1, 2, 3, 4, 5 to the 5th power. Well, this is a lot of extra work to expand it only to simplify it. So let's see if we can generalize a pattern here. So I see I'm multiplying 2 squared times 2 to the third power. My bases are the same. I have a base of 2 and a base of 2. This is very important to remember. Your bases need to be the same in order to do this trick. So 2 plus 3 is 5. So rather than expanding and then simplifying, we could just say that 2 plus 3 is 5 and say that the simple version of this is 2 to the 5th power. So does that work every time? Yes, as long as you are multiplying numbers that have the same base. So let's take a look at another example. Let's do 4 to the third power times 4 to the fourth power. Now, I'm going to go ahead and take a look at this and see if I can use this strategy that we just developed of adding the exponents. First, I want to see, are my bases the same? In this instance, the base is 4. So yes, that is the same. So if the bases are the same, I should be able to add my exponents to get the correct answer. So let's think. The exponent is 3 and 4. So 3 plus 4 is 7. So if my strategy works, I should be able to simply say that this is 4 to the 7th power because 3 plus 4 is 7. But let's go ahead and expand it and make sure that this works every time. So 4 to the third power is the same thing as 4 times 4 times 4. And 4 to the fourth power is the same thing as 4 times 4 times 4 times 4. Well, let's go back and count them. 1, 2, 3, 4, 5, 6, 7. That is 4 to the 7th power. So, why would we do all of this when we could just type that in the calculator? Great question. Well, the answer lies in variables. What if I had a to the third power times a to the fifth power? I can't just type this into the calculator, so I'm going to have to use a strategy to come up with an answer. So let's look and see if we can make this strategy work here. The bases are the same. I have an A and an A. So 3 plus 5 is 8. So the answer to this should be A to the 8th power. But let's go ahead and look and make sure that our strategy is still playing out well for us. So A to the third power is simply A. I'm going to use a times symbol like this, times A, and then A to the fifth power, 1, 2, 3, 4, 5. So let's go ahead and count them. 1, 2, 3, 4, 5, 6, 7, 8. A to the 8th power. So if our bases are the same and we are multiplying, then we can take the shortcut by adding the exponents. All right, so all of the problems that we do with exponents are not going to involve us multiplying them. So let's take a look at some division ones. So let's go ahead and expand this and see what happens. 2 to the 5th power is the same thing as 2 times 2, 5 times. All right, and then 2 to the 3rd power would be 2, 3 times. So let's take a look here. Now, I know that 2 divided by 2 is 1. So if I look at this one, I can say that this 2 divided by this 2, that's 1. This 2 divided by 2 is another 1. and another 1. So I can cancel those out because 2 divided by 2 is equal to 1. So what I'm left with here is 2 squared, 2 to the second power. So now let's take a look back over here where we started and see what we might do. My bases are the same. This is important information. My bases are the same. And my exponents are different. I have a 5 and a 3. So 5 minus 3 is 2. So if my bases are the same and I am dividing, then I can take a short way around and subtract the exponents. So 5 minus 3 equals 2. And that gives me the exponent that I need here. So let's think about another one. Maybe let's do 4 to the 5th power over 4 squared. So if we expand this out, 4 to the 5th power is 4 times 4 times 4, 5 times. And then 4 squared is 4 times 4. So if I'm looking at this the same way, I should be able to say that 4 divided by 4 is 1. So that cancels out. I have another 4 divided by 4, and that's 1. So this cancels out. What I'm left with now is 4 to the 3rd power. So I'm going to say that the answer to this one is 4 to the 3rd power. Well, looking back over here and at my shortcut that I looked at up here, I can see that 5 minus 2 is 3. And so the 3 is my exponent. Remember that the base always needs to stay the same. Okay, so again, we could just put this in our calculator. Why not just say 2 to the 5th power divided by 2 to the 3rd power equals and get an answer? Well, in algebra, remember, we're not always going to be using numbers. Often we'll be using variables. So let's take a look at a variable example. Let's use t to the 3rd power divided by t squared. So let's come back and take a look. T to the 3rd power would be t times t times t. T squared would be t times t. So now we need to take a look and see what is t to the 3rd power divided by t squared? Well, t divided by t is 1 because anything divided by itself is 1. Another t divided by t is 1. So all we are left with is t to the 1st power, or t. So if I use this strategy that we've developed over here, I can say that 3 minus 2 equals 1. And we had 1 t left over here. How about one more of these? Let's do m to the 8th power divided by m to the 4th power. So go ahead and see if you can, in your mind, decide what is the answer going to be. Using the strategy that we developed, we should be able to say 8 minus 4 because our bases are the same, and we can say that if our bases are the same and we're dividing, then we can subtract our exponents. So I think that the exponent is going to be 4. So let's go ahead and expand this out and make sure that our strategy is still working for us. M to the 8th, 1, 2, 3, 4, 5, 6, 7, 8. And then we are going to divide that by m to the 4th. 1, 2, 3, 4. And so m divided by m is 1. Anything divided by itself is 1. So m divided by m is 1. I can cancel these out. And what I am left with right here is 4 m times m times m times m's. So the answer then is m to the 4th power. Again, our strategy does work. So there is another type of exponent problem that you may come across, and that is when you raise a power to a power. And what we have to do when we come to this situation is stop and think, what is actually happening here? So I'm going to start with the innermost part of this problem, and I'm going to say, I'm just going to look at 2 to the 3rd power, and I'm going to keep it in parentheses. So 2 to the 3rd power is 2 times 2 times 2. Now, I'm going to go ahead and let's put this exponent of 2 up here. Now, that 2 tells me that I need 2 groups of what is in that parentheses. So I need to do this twice. So I need 2 times 2 times 2. I need it 1 time, but then I also need it another time. So when I did this, what I have here is 1, 2, 3, 4, 5, 6. I have 2 to the 6th power. So let's take a look at this. I have a 3, an exponent of 3, and an exponent of 2. So 3 times 2 is 6. So when I'm raising a power to a power, I'm going to multiply. So let's take a look at another example. Let's try 4 to the 3rd power raised to the 3rd power. That's a lot of 3's. So 4 to the 3rd power would be 4 times 4 times 4. Now, I need 3 of these groups right here. So this is one group. Let's do another. That's 2 groups. I need 3. So now I have 3 groups of this 4 to the 3rd power. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 4s, so it's 4 to the 9th power. We'll notice that 3 times 3 is 9. So when I'm raising a power to a power, I can multiply. So let's look at what this looks like when I have a variable. For example, let's have a to the 3rd power, and we will square that. So I have a times a times a. This is a to the 3rd power. And I need 2 of those. I need 2 of this group right here. So that is a times a times a. 1, 2, 3, 4, 5, 6 equals a to the 6th power, because 3 times 2 is 6. So these are very helpful strategies, but it is very, very common to forget when to use each rule. So if you forget which rule to use, don't sweat it, just expand it. All right, so let's go back and just make sure we remember. When we are multiplying exponents and the base is the same, we can just add the exponents. When we're dividing exponents and the base is the same, we can subtract. And when we're raising a power to another power, we can multiply.
We need to be able to use numbers expressed in the form of a single digit times an integer power of 10 to estimate very large or very small quantities and to express how many times as much one is than another.
Scientific notation is a method of expressing very large and very small numbers as a product of a number greater than or equal to 1 and less than 10 and a power of 10. So let's talk about why do we even need scientific notation? Why can we not just write the number as it is? Well, let's take a look at these two examples. The distance from the Earth to the Sun is about 93 million miles. Now that's a very, very large number, and it has so many zeros, and every time I write 93 million miles, I have to count all of those zeros. So there is a strategy that would help us to write this and not have so many zeros to count and figure out. So scientific notation helps us do that with very, very large numbers. A typical human hair has a diameter of 25 millionths of a meter. This is a very, very small number. Again, I find myself counting all of these zeros. And so scientific notation can help us write this very, very small number in a way that's easier to read. So let's take a look at an example and talk through how to find scientific notation. So the first step in finding the scientific notation is going to be to find the number that is between 1 and 10. Remember, our definition said that it had to be the product of a number greater than 1 but less than 10. So if I'm going to look at this number right here, 34,600, I need to think about what number would be less than 10? So it would be 3. So the number between 1 and 10 would be 3.46. Because if I moved the decimal right here between the 3 and the 4, that gives me a number that's greater than 1 but less than 10. So now I need to think about, well, how did I get there? Well, what I did was I simply divided this 34,600, I divided it by a power of 10. So we can find that by counting. Originally, the decimal was back here behind this last zero. When I move it one decimal place, that's 1 power of 10. Moving it again tells me that's 2 powers of 10, 3, 4. So when I have the decimal here between the 3 and the 4, the power of 10 is 4 because I had to move it 4 times. 1, 2, 3, 4. So the number in scientific notation, I'm simply going to take the 3 and 4600ths, the 3.46, I'm going to take that number and I'm going to multiply it because remember our definition said that it was the product. So I'm multiplying it by 10 and we found out that it was the power of 4. And so that's it. This is how we find scientific notation. So let's take a look at another example. So I have 125 million. So I want to look at this and I need to think, what is the number between 1 and 10? So I need to find this number, and it would happen if I put my decimal right here. So that would give me 1.25, would be the smallest number that I can make that is between 1 and 10. So let's really quickly take a look and make sure we understand why it has to be in this spot. If I put the decimal here, I would have 12.5, and that is a number that's greater than 10. So I need to make sure that I get it all the way over so that the number is less than 10. Okay, so now I've found my number between 1 and 10. Now I need to find the power of 10. So to start with, my decimal is right here behind the last 0. So each time I move the decimal, that is 1 power of 10. So 1, 2, 3, 4, 5, 6, 7, 8. So the power of 10 is 8 because I moved the decimal 8 times. 1, 2, 3, 4, 5, 6, 7, 8. So to write that number in scientific notation, I need to first use my number that was between 1 and 10, and that was 1.25. And remember that the definition of scientific notation is it's the product of a number between 1 and 10, this, and product means we're multiplying, and a power of 10. And this time our power of 10 is 8. So now let's go back to that first example, the reason that scientific notation is important at all. Right here, the distance from the Earth to the Sun is about 93 million miles. So let's talk about how we would write this in scientific notation. The first step is to find a number between 1 and 10. So if I do that, it is right here, 9.3. So the second step then was to find the power of 10. And we do that by looking at how many times we divided by 10 or moved the decimal. So 1, 2, 3, 4, 5, 6, 7. So 7 times we moved the decimal. So going back to our definition, the definition of scientific notation is the product of a number between 1 and 10. So we know that in this case, it's 9.3. And it's the product, that means multiply, of a power of 10. And in this case, it's 1, 2, 3, 4, 5, 6, 7. All right. So that is 93 million miles in scientific notation, 9.3 times 10 to the 7th power. So now we also have to be able to go the other direction. And so we have right here, I'm going to bring this down because it's a little bit hard to fit everything in. So right now we have a number that is between 1 and 10. And we have the product of the number between 1 and 10 and its power of 10. So the first thing I need to think about how to undo what we did here. So I have the power of 10. Let's move that decimal back So when we were changing something into scientific notation, we moved the decimal to the left. So now to undo that, we need to move the decimal to the right. So my decimal is right here between the 5 and the 9. And so I need to move that decimal back up by a power of 4. So let's count that. 1, 2, 3, 4. So my decimal is going to go here. I need to add something in these blank spots. And so I can remember what I moved away when I went to a power of 10 was I took out these zeros. So I just need to put the zeros back. So let's put a couple of zeros back in each of these spots where there was nothing. So now I'm going to rewrite this number. I don't use the decimal here anymore. I simply copy everything else as it was. So I can also go back and put a comma here. It helps us to read the number correctly when we see a comma there. So this is 59,600. And we did that simply by undoing what we had done before. So now let's take a look at this one. We have the product of a number between 1 and 10 and a power of 10. So right now, I don't see a decimal. And it's important to remember that the decimal is always after that whole number there. So let's put the decimal there. And now we just need to move the decimal by a power of 10. And our power of 10 this time is 8. So let's just move it. 1, 2, 3, 4, 5, 6, 7, 8. So our new decimal is going to be way back here. And in each of these places where we moved the decimal, we need to add zeros, just like we did up here. So I'm going to add 1, 2, 3, 4, 5, 6, 7, 8 zeros. Now this is a very large number to write, so it definitely is beneficial to write it in scientific notation. So let's go back and let's write it in standard form. So we had 3 and 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And then let's just add the commas. 1, 2, 3, comma. 1, 2, 3, comma. All right. So now we need to think about really small numbers and going in that direction. So when we have a very, very small number, we're going to use the same process. But when we had a large number, the power of 10 was a positive. So now that we have a very, very small number, we'll use a negative power of 10. So let's take a look. Right here, I need to figure out where would I put a decimal so that I have a number between 1 and 10. So I would have to move the decimal back to right here. So my number now is 7 and 1/10, or 7.1. Make sure that you rewrite this and look at it carefully to make sure that it's between 1 and 10. All right, so now we need to count the power of 10. So I'm going to start with the decimal, and I've got to go until I get right here behind my 7. 1, 2, 3, 4, 5. So my power of 10, I moved it 5 spots, but now let's remember, we moved backwards. And so that is going to be a negative 5. So now our number in scientific notation, remember that the definition for the scientific notation is the product of a number between 1 and 10, which in this case is 7.1. And product means multiply. And the power of 10 is a negative 5 because we had to move the decimal backwards. We were actually multiplying. All right, so now let's take a look at another example like this. Again, here we have a very, very small number. And so we need to think about what is the number that is between 1 and 10. So as I think about this number right here, here's the decimal, and I've got to move it back so that my number between 1 and 10 is right here at 1.23. So 1.23. So now let's count and see how many decimal places we had to move it. So 1, 2, 3, 4, and 5. I moved it 5 decimal places. Now remember, since we're going backwards, the power of 10 is negative. So remembering that we need to do the product of a number between 1 and 10. So 1.23. And then it's multiplied by a power of 10. So here is the 10. Our power of 10 right now is negative 5. All right. So now let's go back to that first example that we looked at where we had a example about a human hair. So the typical human hair is 25 millionths of a meter. So now let's write this in scientific notation. So I first move the decimal to where I have a number between 1 and 10. And in this instance, that's 2.5. And then I need to count how many places I needed to move that. So let's move it. 1, 2, 3, 4, 5, 6. I moved it 6 places. Let me go ahead and write that right here. I'm going to put a negative 6. Remember, we're going backwards, so it's negative. That way, when I go to write the number out, I can actually remember it. So I have 2.5. And remember, we're going to multiply by a power of 10. And the power of 10 in this case is negative 6. All right. So the reason that we use scientific notation is to express very, very large numbers and very, very small numbers a little bit easier. All right. So remember that scientific notation is the way that we can express numbers as a product of a number greater than or equal to 1 and less than 10, and a power of 10.
So in addition to expressing numbers in scientific notation, we also need to be able to perform operations with these numbers, including problems where both decimal and scientific notation are used.
Scientific notation is very, very useful in representing very large numbers as well as very small numbers. But we also need to be able to use scientific notation to compare these types of numbers. So if we were thinking, for example, about the population of the United States and the population of Canada, how are they different? What's the total population? What's the difference in the population? So we need to be able to operate with these effectively. So let's talk about how to do that. So this example shows that we are going to add the two scientific notations. So the scientific notation to start with is 4.4 times 10 to the 13th power plus 3.02 times 10 to the 13th power. So the first thing that we need to think about when we are adding and subtracting scientific notation is that it's very simple as long as the powers of 10 are the same. It's very important to make sure that the powers of 10 are the same when you're adding and subtracting. So let's take a look here. The power of 10 in the first part is 13. The power of 10 in the second is also 13. So we can start and just add the powers of 10 because they both have the same power of 10. So we'll start by doing 4.4 plus 3.02. And when I add these two together, all we have to do is add. 4.4 plus 3.02 is 7.42. And then all we have to do, since these are the same and we are adding, or also this works with subtraction, is keep that power of 10 the same. And remember that scientific notation is the product of a number between 1 and 10 and a power of 10. So looking right here, I need to make sure that this is between 1 and 10, and I see that it is. 7.42 is greater than or equal to 1, but still less than 10. So that is all I have to do when I add scientific notation. But let's take a look at another example, because this one was easy. It started out, both powers of 10 were the same, and then when I got my answer, it was already a number between 1 and 10. So let's take a look at another example. So 1.2 times 10 to the 5th power minus 9.5 times 10 to the 4th power. Remember, it's important that the power of 10 is the same with both of the things that I'm adding or subtracting. And in this case, it is not. So I need to adjust my expression so that these both have the same power of 10. In order to do that, I need to change one of them. I'm going to start by changing this one. It's easy to make this something times 10 to the 5th power by simply moving a decimal. So let's do that. I'm just going to move the decimal one place and put it up here. So my new expression that also adds right here, I've changed it to a 5 by moving the decimal. So my new expression then is 1.2 times 10 to the 5th power minus 0.95 times 10 to the 5th power. And it has changed because I moved my decimal, and that made my exponent change here. Okay, so the first thing we had to do was make sure that our powers of 10 were the same. Now we can just subtract. So let's take a look here. I'm going to subtract 1.2 minus 0.95. And when I do that, I get 0.25. And I just bring down my power of 10, and I keep it the same. And remember, that is the product. Okay, so now let's make sure that this is in scientific notation before we say this is our final answer. Remember that in order for it to be in scientific notation, it has to be the product of a number between 1 and 10 and a power of 10. This number right here, 0.25, this is not in scientific notation. So I am going to have to change it to scientific notation by moving the decimal. So when I take this decimal and I move it one place over here, I've moved it backwards. And so that means that I need to take a power of 10 away. So my answer is 2.5 times, remember we've changed this, 10 to the 4th power. All right, So when we add and subtract, we can subtract and add directly, as long as our power of 10 is the same. If it's not the same, we just change it. And then once we get our answer, we have to make sure that it is a number between 1 and 10. So now let's talk about multiplying and dividing. Now, our powers of 10 do not have to be the same in multiplying and dividing. All we need to do is remember the exponent rules that we talked about earlier in this video. When we multiply, we can add the exponents. And when we divide, we can subtract them. So let's start by looking at the first part of this expression. 1.8 and 6.7. When we multiply 1.8 times 6.7, let me just write that over here so that we remember. We're multiplying 1.8 times 6.7. When we do that, we get 12.06. So let's go ahead and write that down here. 12.06. Because this problem is asking us to multiply, we simply multiply those first two numbers. So now we need to deal with the power of 10. Remember from earlier, when we multiply exponents, we can simply add them. So I'm going to go ahead and write multiply times 10. So we can say that the power of 10 is going to be 9 plus 12. So 12.06 times 9 plus 12 is 21. Oops. Times 10 to the 21st power. Okay, so the next step, the last step that I need to think about is I need to make sure that this is scientific notation. Remember that scientific notation is the product of a number between 1 and 10 and a power of 10. As I look at this, I notice this is 12.06. That is greater than 10. So I'm going to have to switch this number, move the decimal so that it is between 1 and 10. So if I move the decimal one place and put it right here, that gives me a number that is between 1 and 10. But I also have to change this power of 10. Because I moved this one place, I have to add 1 here. So my answer is 1.206 times 10 to the 22nd power. All right, so the first thing that we had to do when we're multiplying scientific notation is we're going to multiply the first part, 1.8 times 6.7. And then, remembering our exponent rules, we're going to use those to combine the 10 to the 9th power and the 10 to the 12th power. And we do that by saying 9 plus 12. And so our power of 10 is 21. But then we had to look and make sure that our first number is between 1 and 10. So we saw that that wasn't correct, so we had to move the decimal, and that also changed our power of 10. All right, let's take a look at another example. Here, we have a division problem. We're going to do a very similar process and make sure that our answer that we get is in scientific notation. So the first thing that we need to do is simply divide. So we're going to divide 3.46 divided by 2. When we divide 3.46 by 2, we get 1.73. And I'm going to go ahead and write times 10. And let's figure out the power of 10. Remember, when we divide exponents, the shortcut is to subtract them. So 17 minus 9 is 8. All right, so 17 minus 9 is 8. We have a power of 8. So now let's go ahead, let's think through our checklist to make sure that this is correct. First, we divided 3.46 divided by 2. We got that. Then we used our exponent rules to find the power of 10. So the last thing that I need to think about is I need to make sure that this number is, in fact, a number between 1 and 10. So right here I see 1.73. That is between 1 and 10. So we know that this is now the answer. So let's go back to this first example that we looked at and see how we could use this in a real world situation. So right here we have the United States and Canada, their populations. And I could combine them to say how many people live in the United States and Canada together. So let's go ahead and let's do that example there. We have 3.1 times 10 to the 8th power. And I'm going to add 3.38 times 10 to the 7th power. So now, our first step was to make sure, we're adding. Sorry about that. Our first step was to make sure that the power of 10, when we're adding, the power of 10 needs to be the same. So what I need to do is I need to think about, I have a power of 8 here and a power of 7 here. I need to change one of these so that the power of 10 is the same. I'm going to change Canada's. So when I do that, I move this decimal one place, and I need to change this to an 8. So I've moved the decimal, and now it's a power of 8. So rewriting that, I have 3.1 times 10 to the 8th power plus 0.338 times 10 to the 8th power. So the rule says that when we get to this point, we can simply add. So let me put it over here so that we can make sure that we see what's happening. 0.338. So if I put these together with addition, I get 3.438. And then remembering that it needs to be times the power of 10, I'm going to do times 10. And the power of 10 is 8 in this situation. So times 8. Now, checking to make sure that this number is actually in scientific notation, the 3.438 is a number that is greater than 1 and less than 10. So I can use this. Thank you so much for taking your time today and doing math with me. I hope that there was something that you remembered. And if you have any questions about the content that we covered, please contact me or your teacher, because we're here to help you and we want to make sure that you continue to learn and grow while we're away. I hope you have a great week. Goodbye.